Welcome to the central force problem, a discussion based on the third chapter of Herbert Goldstein's treatise, Classical Mechanics. Today we are going to discuss a brief introduction to the chapter and the reduction to the equivalent one-body problem. The dynamics of two bodies moving under the influence of a mutual central force is presented as an application of Lagrangian mechanics. As will be shown, the study can be thorough even when complete solutions are not available. Specific topics include applications to thermodynamics and statistical mechanics, astronomy, classical scattering theory, and a short overview of the difficulties introduced by the three-body problem. So, in terms of the reduction to the equivalent one-body problem, we investigate a monogenic system of two particles of masses m1 and m2 interacting through the generalized potential U, which will depend on the relative vector between the particle, possibly on the relative velocity between the two particles, and also in principle higher order derivatives. Such a system has 6 degrees of freedom and is therefore described by 6 generalized coordinates, which will be the components of the radius vector for the center of mass and the components of the relative vector between the two particles. So in this case, the Lagrangian is simply the difference between the kinetic and the potential energy given by the generalized potential U. The kinetic energy, as we have seen in the previous chapter, can be decomposed into the kinetic energy of the center of mass and the kinetic energy of motion about the center of mass, which in turn has the expression here being given just by the kinetic energies of the two particles, where the velocity is just the velocity relative to the center of mass. So these two vectors relative to the center of mass are just given by the difference between the radius vectors of the two particles relative uh, to the laboratory frame and the coordinates of the center of mass, and it follows immediately that they are up to a constant equal with the uh, relative radius vector. And then obviously we can easily take the time derivatives in these two expressions and then plug them into the relative kinetic energy to obtain the expression here, which together with equation 3.1 leads to the following expansion of the Lagrangian. In a kinetic energy term, of the center of mass itself, the kinetic energy of relative motion about the center of mass in terms of the square of the relative velocity between the particles, and the interaction energy. Now notice that this Lagrangian does not vary explicitly with the coordinates of the center of mass, so the radius vector of the center of mass itself has components which are cyclic coordinates. In other words, the momentum of the center of mass itself is conserved, so the center of mass is either at rest or moving uniformly, and as such can be dropped from the subsequent discussion. So we can forget about the first term, and then the Lagrangian is simply given by the relative kinetic energy of the two particles and their interaction. And this can be seen as the dynamics of a single particle moving in a potential which can possibly depend on its position and its velocity and so on. A particle of a mass named reduced mass, which is given by the expression here. So the product of the two original masses divided by their sum, or equivalently its inverse, is given by the sum here. In conclusion, we have introduced a broad class of physical phenomena that can be treated as central force problems. And then we have shown that the central force motion of two bodies about their center of mass can always be reduced to an equivalent one-body problem in terms of their relative coordinates and the reduced mass. And in the following, we will derive the equations of motion and first integrals of the central force problems. That being said, I want to thank you very much for watching the video. I hope you found it worth your time, and I will catch you later. Goodbye.